When we observe circular motion, viewing it from top down, the circular motion has objects moving at a constant speed around in a circle. But if we look at it side on, so look at the side view, the object appears to go faster in the middle and slower at the extremes. This is because we are viewing one component of the displacement. If we trace this on a moving sheet of paper, we would draw a sinusoidal wave. And this allows us to use the same language in circular motion and waves. The equation for displacement is that since x equals x naught sine delta theta, and we also know that omega equals delta theta over t, so x equals x0 sine omega t. Now let's link it a little bit closer to the sine wave. Going around one complete loop makes us go from a peak to an adjacent peak, for example. So going around one complete loop goes round 2 pi radians. Going from a peak to an adjacent peak is equivalent to 2 pi radians. Going from a peak to a trough is equivalent to pi radians. And going from a peak to an equilibrium line is pi over 2 radians. The difference between these positions, so 2 pi and pi over 2 for example, the difference between them is called the phase difference. So phase relates to the position of a point on a sinusoidal wave. Phase difference is a difference between the positions of 2 points on a sinusoidal wave. One final point is that in a specific case where circular motion repeats, that means it's periodic. And if it's periodic, we can talk about frequency. So in this specific case of angular speed, omega equals delta theta over t, which equals 2 pi over capital T for one complete cycle, which is equal to 2 pi f. In this case, omega is called angular frequency, but it's angular speed really.